Now that we understand a little more about streamlines, we're able to derive Bernoulli's equation. Bernoulli's equation is a commonly used fluid mechanics equation. It's very useful for situations such as pipe flow and flow over wings to understand the pressure distribution induced by flows. To find Bernoulli's equation, we're going to take Euler's equation and we're going to take the dot product of u with each term in the equation. So taking the dot product really gives us an energy equation. On the left hand side we take u times capital du dt, and if we bring this u inside the derivative here, we just end up with half ddt of u squared. On the right hand side we have u dotted with gravity minus u dotted with the pressure gradient. The next thing I'll do is I'm going to assume that I can write the body force, or the gravity, as a potential. And to do that I just write G is equal to grad of capital psi, where capital psi is the potential field, not to be confused with the stream function lowercase psi. And we know that for the case of gravity that this potential field is just negative G times Z. And now, by expanding out the total time derivative, we can write the left-hand side as the local rate of change of the kinetic energy, plus u dot grad of the kinetic energy is equal to negative u dot grad of gz minus u dot grad of p on rho. All we need to do now is assume that the flow is steady, in which case the local kinetic energy won't be changing in time, or ddt of half u squared is 0, and we end up with three terms that all have a u dot grad in front of them. And this is Bernoulli's equation. U dot grad of half u squared plus gz plus p on rho is equal to 0. Now remember that u dot grad psi is 0, where psi is the stream function. And it's for this reason that Bernoulli's equation is often interpreted as conservation of energy along streamlines. In other words, if you follow a streamline, then half u squared plus gz plus p on rho is constant. And the physical consequence of this is that if you have flow going along a pipe and the height of the pipe is not changing but the pipe narrows off, then the velocity must increase, and that means there must be a corresponding decrease in pressure.